Nope. Howdy, everyone. Carl, you were not late. You were right on time. I actually started this a little early because I was just anxious. Um, so, um, so if you could let me know if the audio is good, if the visual is good, that sort of thing, I would appreciate it. Um, Thank you, Carl. That was done by Steaming Cup of Reason, or Jeff. That's actually one of the intros that he did for me. I just wanted something so that I didn't just pop on the screen. So, um, so yeah, if you can give me a thumbs up to let me know if the audio quality is, okay, good. Thank you, Carl. Yes, let me say hello to Dora, Tusk, Carl, and who else? Is there anyone else in here? I think that's all we have at the moment. But thank you all for. Oh, George. I knew there was someone else. Thank you all for coming. I really appreciate you being here for my inaugural. Oh, and Jess is here. I haven't seen you in a bit. It's been a minute. Thank you all for being here for my inaugural, I guess, OBS. OBS? Is that what this thing is called? OBS stream. I've, for reasons, mainly because my Windows machine decided to crap itself, I switched over to Linux, and so I found that OBS is actually a much better system than StreamYard. So I'm still getting the hang of it, but I think I've got what I want set up. So before I get into everything, hi Ark, welcome to the stream. Appreciate you being here. Before we get into the meat of what I'm going to be talking about, yeah, IBS is not something. No. Before we get into the into what I'm going to be talking about or babbling on about, I unfortunately decided to waste a little bit of time on Twitter right before I came on, and two things popped out almost immediately. First thing is an article by Space.com where the cosmonauts on the ISS are trolling Ukraine by holding up flags of the two provinces that Russia has now recently taken over. I'm not going to try to butcher their names. One starts with an L, the other one starts with a D. And so, yeah, the Russians are now using the International Space Station as a platform to promote Russian propaganda. Fantastic. And then, not only that, I see a tweet by my favorite individual, Elon Musk. And I've mentioned this to other people. I don't know if I've mentioned it on stream, but I have a new life goal. It's not something that's prominent. It's not something that I'm going to really try my hardest at it, but it is still a life goal. My life goal is to troll Elon Musk on Twitter enough that he notices and blocks me. So, getting back to Mr. Musk, today, an hour ago, he tweeted just this: flatulence earther. My response was, "What are you, 6? I sincerely hope that you mature past the point that fart jokes are funny to you." So yeah, the richest man in the world has time to tweet that shit. All right, I'm off with that. No. Mr. Musk is certainly not my favorite individual in any way, shape, or form. I can go off on that. I think I have in a previous stream, but that's not what we're here for today. What we're here for today is really I want to talk to all the flat earthers out there, all the people in the flat earth community. Now, I have, aside from my discussion with Sleeping Warrior, I really don't put out content that directly talks to folks of the flat earth. Really what I want to do is I want to put out content that is strictly educational, that both people of the flat earth and everyone else can enjoy and get educated by. So, is your goal to lick him? No, my goal is not to lick. Yeah, Carl, I know that they aren't listening, but I'm hoping against all hope that eventually one of these videos will sort of go viral, as it were, get noticed by a flat earther somewhere, and then get commented on. I'm hoping, because I'm actually talking to flat earthers in this video, that will happen, rather than them trying to pick apart one of my lectures, which I would really be very interested in doing. So, this might be becoming a thing. So, what I'm envisioning is, whenever I get bored and can't sleep, like tonight, I'm going to put together a video entitled "Dear Flat Earth, Something is a Thing." So tonight this morning is space is a thing. Next one I've got in mind is gravity is a thing. And I will actually approach that problem a little differently than everyone else seems to be, or the debunking community seems to be, which is everyone seems to go off on about Cavendish this, Cavendish that, when really Galileo's inclined plane and simple pendulums essentially illustrate gravity pretty well, and they are not nearly as complicated as Cavendish. But I digress. So, when I encounter flat earthers, and occasionally I am a member of the 24/7 Flat Earth Discord. I'd like to get on the one with Bev. Like is probably too strong a word. But I'm on there, and so I've actually gone on and gotten onto their live stream Discord thingy-do, and had discussions with them. And so, inevitably, the discussion I had with them is I get confronted with the same thing I get confronted by any other flat earther when I tell them that I am a professional astronomer. Is, you are not a scientist. They come back with, you are not a scientist, you don't do actual science, and everything that you do, and if they're more mean-spirited or less kind, I guess, they will straight up tell me that everything that I've studied is pipe dream and fairy tales, or, to coin a phrase by Sleeping Warrior, unicorn farts. So what I'd like to do is, I'd like to sort of address that in a couple of different ways. Hopefully I am awake enough to actually make a coherent argument. I want to do this in a couple of different ways. First off, I want to really beg the question. In the lower left, as you can see, these are observations that I have taken or I have been in the room when these observations were taken. Now, this spans basically a decade worth of stuff that I've done. If any of you have any questions about the images themselves, I'd be happy to. Really, the first thing that pops out to me when I look at these is, wow, I am really bad at astrophotography. But the other thing that point out to me is that that pretty much shows these are not CGI. If I were going to make CGI images, I sure as hell would make images that look better than that. Maybe I'd make an image that looks like the one on Wikipedia, which is the Orion Nebula. I also have an image of the Orion Nebula in this slideshow. So that's a Bart spiral. That's the moon. I actually I have like 16, 18 images of the moon where I have mosaicked them, and I actually created a full first quarter moon image from it. It's very that was an interesting first time I actually mosaicked something. But point is, there's the Orion Nebula. So yeah, you could compare my work to Hubble. The thing is, these are observations. These are images. Yes, the telescope that I used was the telescopes I used ranged in size between 24 inches and 32 inches. 20 inches and 32 inches. I try to block out LSU as much as I possibly can. But the issue is, so these are things that can be done by people on the ground, on Earth, and I have seen far more spectacular images taken by people with much smaller telescopes that are within the financial reach of the enthusiast. That's the sun, by the way. I was there when I took that. We have the honor of actually having a solar telescope, a telescope that is protected against the sun, so we can actually directly observe it. And so, I really need to stop saying so. I almost did it again. Where was I going with this? So yeah, these are images. These are images that you can buy a telescope, for a reasonably inexpensive telescope, and you can slap a DSLR camera on the back of it, and you can take amazing pictures of these things. And so my first question to any flat earther, or anyone in the flat earth community, is, why do these exist? These do not exist. These cannot be seen, aside from the sun and the moon, these cannot be seen without the aid of a telescope. So, let's just say that there is a designer, God, whatever, who did this. Why would they create structures in the dome, these luminaries, that we cannot see without the advent of telescopes? And these images are consistent from one observer to the other. They're not subjective. And then we can study these things, and we can get real data from them. And that data is consistent. And that ties into another part of why I am not a scientist in their view. I am not a scientist in their view because I cannot physically manipulate the sun, the Earth, or the sun, the moon, galaxies. And because I would not doubt that, Tusk. Because I can't manipulate it, because I cannot physically touch these things, then it's not science. It's pseudoscience. It's just pie in the sky thinking or what have you. But if that's the case, if that really is the case, then why is it that, well, one, there are tens of thousands of astronomers across the globe. There are tens of thousands of astronomers across the globe. It's an international community. We, for the most part, talk to each other without limits, although there is some political shenanigans going around, particularly between the United States and China, but I digress. But we all get together, we all talk to each other, we all share our work. And for the most part, astronomy is extraordinarily self-consistent. We can get distances to, say, for example, the Andromeda Galaxy. The Andromeda Galaxy. Oh, and as I found out by watching, unfortunately, a Jeranism video, my first Jeranism video, earlier yesterday, I was reacquainted with the idea that apparently folks do not believe in astronomy because big numbers. Jaron was talking about the distance technique of stellar parallax. This is one of the rungs that allows us to determine the distances of stars that are reasonably close by, or at least astronomically close by. And all he really had to say was, he just derisively said, no, this doesn't work because the distances are too big. Like, okay, all right, fair enough, I guess. But if I can use radar finding on an asteroid, and it tells me that asteroid is, say, 1.5 AU from the Earth, and then I use trigonometric parallax, which is a completely different technique, and lo and behold, I get a distance of 1.5 AU, why is that? Why would I get two consistent values using two disparate methods? Why is the universe created that way? If it isn't physical, if there is no physical, if there is no physical underpinning to things in space. You can also say the thing on the Andromeda Galaxy. The Andromeda Galaxy, you can use the Cepheid luminosity, the period luminosity relationship with pulsating variables, specifically Cepheids, and you can get a distance that way. Then you can also use the technique called spectroscopic parallax, which I really won't get into. If you're curious, I just posted a lecture about it on ASTR 113 lecture series. On that, I talk about the distance ladder in more detail. But anyway, these, again, are two disparate techniques. They are not the same. They don't use the same underlying principles. And they get the same result, or results which are consistent with each other. Yes, there are open questions. And the big one is that often gets thrown at me is dark energy and dark matter. Dark matter, if you look at it, that is very consistent. Dark matter must exist. We have seen it in spiral galaxies and rotation rates of spiral galaxies, in the dispersion velocity of stars in elliptical galaxies. We've seen it in X-ray comas of galactic clusters, and we've seen it in the motions of galactic clusters. We have seen this in a variety of different states where there is matter present which we are not seeing. What dark matter is? No idea. I'm putting my money on neutrinos, but I suck at gambling, so you probably don't want to do that. Dark energy? Yeah, no idea. I don't think anyone really has any idea about dark energy. But that's what's cool about science, is that it is not definitive. It is not, okay, this is what it is, and we're done. Science does not claim to know everything, because which is good for me, because if it did, I might be out of a job. It's great job security when you have never-ending questions. And that's what I find to be most noble about astronomy, and really any science, is that constant drive to ask the question why, to go further than what we know, and explore. Really, just not close ourselves off to a defined worldview, to a worldview of mistrust, a worldview of that is limiting. I find it ironic that a number of people in the flat Earth community are professed Christians, and they say, particularly CC, this was God's creation and what have you. Like, God's infinite. To say that he only created just the Earth and the dome around it seems to be limiting God in a really big way. But I'm going to step off the theology for a second, or for a moment. I find it odd that folks that go to divine or a divine source to explain their worldview often end up limiting that divine object or that divine source. There's probably something very profound in that, but I have no idea. Dark energy is entropy at work. I don't know. All I can really tell you is that dark energy is a negative pressure. It is essentially a repulsive pressure outside that is basically counteracting gravity, which is a thing, by the way. And next one of these streams, I will go off about that. And I will talk about the inclined plane, the pendulum, and my personal favorite, planets going around the sun. Density disequilibrium cannot explain planetary motion. And again, if space were not a thing, if you want to go with the idea that, oh, these planets, these are just luminaries that just happen to be in the Earth or in the dome, why do they behave empirically as Kepler's laws describe them? This is not derived math. This is not what Newton did and said, all right, I have this idea of gravity, let me play with it and see what I come up with later. Kepler looked at the motions of these planets, specifically Mars, and he mapped out the orbit of Mars. And by looking at other planets, he was able to come up with his harmonic laws. These are not derived laws. These are empirically, these are directly observed things. So again, my question to the Flat Earth community is, why? Why is it that if you take the period, the relation or the ratio of the period of the Earth's orbit to that of Mars, and you square that quantity, why is that equal to the semi-major axis or size of the Earth's orbit divided by the size of Mars' orbit, that quantity cubed? And you can choose any two planets you like. That holds. So again, question is, why? If space is just unicorn farts, then why does all of this seem to make sense? Why does all of this seem to gel with each other to the point that tens of thousands of people have devoted their lives to studying this field and seem to agree on these things? And when I talk about consistency, I'm hopefully I can illustrate that using my own work. Yes. Anyway, so before I get into that, I want to. Where is it? Is it this one? I don't think it's this one. Oh, I was doing so well. That one? Nope. That's there. That's there. Nope. That's not it. Video capture. No. Oh, man. I was going to show you. This is actually... Oh, there it is. Ha ha ha. Ba-boom. I love this. Oh, hey, Clive Wells. Thank you, Clive. You sent me down a rabbit hole of reading my linear algebra textbook, and I thought to myself, why in the hell am I reading linear algebra at 3 in the morning? Although it was great, because I got to learn more about identity matrices and determinants and all that. Got to refresh on that. Anyway, back to what we're looking at here. This is a video, real-time video, taken by my students using the solar telescope. You can see solar granulation. You can see basically what's prominences. So again, why? Why does this happen? And if you're going to talk about science, if you're going to start banding around what is science and what isn't, then you're going to have to, science has to explain things. That's ultimately what science is for, is to explain phenomenon. That's a really good view of the prominence. My students were kind of, this is shaky cam, but anyway. Where was I going with this? So yeah, they have to, so science is in the business of asking why stuff happens, or explaining why stuff happens. So I would ask again, I'm going to ask flat earthers pretty much the same question over and over again, is why does this happen? In your idea of the conception of your worldview, why is this right? Is this reality? And again, this isn't CGI. This isn't made up on a computer. This is direct video taken through a telescope pointing at the sun, and this was done 3 months ago? Something like that. Incredible stuff. Just amazing that we can do this. Granted, the telescope that we're using is very expensive, but there are cheaper versions of this same type of telescope that are kind of within range. We're talking about the 2K range, so I mean, if you go on a payment plan, you might be able to get it. But there are telescopes that are well within the budget of middle class and more affluent folks out there. So this is not some, well-kept equipment that is being hoarded by the government, and you can't use it. So let me take that off. The other thing that I really kind of chaps my butt is, I'm going to try to stop swearing as much as I normally do, is when lay folks come to me and say, you ain't a scientist. Like, really? Do I come to your job and tell you you're not a huge crane operator? You are not a minicab driver? You are not whatever it is QE does? No, I don't do that, because that would be rude and it would be ridiculous. No one, it's like going to a doctor and basically he's like, you have cancer. No, I don't. And you're not a doctor because I don't have cancer. It just, I don't understand that. Where else do you actually really have the nerve to go up to a professional and basically accuse them of not knowing their own subject? Something they have spent years, possibly decades, devoted to that. Has Rob talked about the physics of the dome yet? Not quite. I've talked about sort of the physics of some of the luminaries in there. Telescopes come with images of space pre-installed. Actually, you're kind of onto something there, or at least I'm afraid of this. There's something called an EV scope. Little e, big V, little scope. And it's a nifty toy. It really is a nifty toy. It's expensive as all hell. The cheaper option is about $3,000. The expensive option is about, I just got a quote from it, it's about $5,500, maybe $6,000. And this is a small aperture telescope. But what's really nifty about it is it basically is a camera, a CCD camera attached onto a telescope. And the point of it is for use within a highly light polluted area. So I saw a review about this, and this guy took the scope literally to Las Vegas, the Las Vegas Strip, probably the brightest thing you can possibly imagine at night. And he was right off that strip in a parking lot. And the images that he was getting with this telescope were phenomenal, because he was basically, what was happening is the telescope took an image, waited 4 seconds, took another image, added that to the previous image, and kept going. So it really does kind of, I could easily see how someone was skeptical would look at that and be like, that was just loaded into the telescope. We're not actually seeing But yes, Tusk, I would not be surprised. But again, I would challenge any flat earther or anyone in the flat earth community. I really don't like flat earther. Anyone in the flat earth community. I will loan you a telescope. I will loan you a CCD camera, and I will gladly point it at whatever object you want, give you the coordinates and teach you how to use it, and you can see the same things that I take images of over to the left. So yeah, it's yeah. I don't mean to be persnickety about it. Actually, I do mean persnickety because it really the you're not a scientist, you're not an astronomer, astronomy is bunk, is really kind of wearing on me. But let us move on from there. So, to combat this idea that I am not an astronomer, or that astronomy is not science, let me introduce you to this. Unfortunately, this is not going to work as I'm about to demonstrate, because one of the problems with academia, is that it's not free. The information is not free, with few exceptions. The NMRAS, monthly notices from the Royal Astronomy Society, I think that's what that stands for. That journal is free. You not only can you publish it for free, publish it. They don't ask money to publish in that journal. You can get the articles for free. So just Google MNRAS astronomy, and you can get to their website. You can download any articles that you want. People have published in. Problem with, and those are the Brits. Problem with the U.S. is the major publications, the Astrophysical Journal, the Astronomy and Astrophysics, Nature, not only require you to give them money in order to publish your stuff, but they also charge money for the layperson to actually access that stuff. Now, being at a research institution, we have a license with these journals so that we can download these papers for free. So if any of you are interested, if any of you actually have a know of a paper that you want to read, but it's behind a paywall, just let me know. I can download it, email it to you, what have you. So, what I want to do here. This is the academic version of Googling yourself. So, my name is James Robert Parks IV. I go by Rob for whatever reason. So you know, the world will end under the reign of James Robert Parks the 59th, but those two things are not related. It was not King James's fault that the Earth died. Thank you, Dora, for posting that link. Anyway, that's why I'm Googling, or I put in Parks J, because my first name is Jay. Now, let's put in year 2009. What we're going to do, this is NASA Ads. This is a database, pretty much of all published science in astrophysics. There are other databases that, if you're interested in geology or biology or what have you, there are similar databases that you can access. And so, yes, sadly, I am not on the podium, but I am the last one standing. So I guess there's that. That's actually a little bit morbid, but anyway. Oh, wow, Tusk, that is friggin' impressive. Now, because I tell people, you can call me anything you want to, so long as I look, except for with one exception. There is one thing that I will not answer to that will irritate me if you say it. And people were like, "What is it? What is the name?" I'm like, "My name is James Robert. Figure it out." And it takes them way too long to come up with Jim Bob. Friggin' hate that name. So, yeah, I've just basically given you all ammunition. If you really want to irritate me, just call me Jim Bob. Jimmy Bobby actually doesn't really bother me that much. That reminds me of Ricky Bobby, which, you know, Will Ferrell, I like. Anyway. Yes, Clive, I'm pretty sure you're not going to, you're going to beat that baby shark into the ground. So, yes, so let's get back to stroking my ego. So, I put in Parks J, 2009, because that's essentially... yeah, I know, Tusk. 2009, because that's essentially where I really started publishing, or was involved in research that was published. So, let's search. Dun, 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 and we get these results. Now, admittedly, not all of these are me. And I will also admit that I only have two first author papers, and I will highlight those. All the rest of these, I am third author or just part of the gang that helped out. So, what I wanted to, one of the first author papers that I published, probably the most meaningful to me, is interferometric imaging of Lambda Andromeda. That's half of what my thesis was about. So, yeah, I know, Dora. So let me see. I've already pulled it up. Is that it? Nope. Is that it? Nope. That one? Nope. That one? There she is. There's my baby. All right. So, what are we looking at? This is a paper I wrote. Took far too long for me to actually get this thing published. It was published in 2021. To give you an idea, the data was collected in 2010, 2011. Not the typical route that most astronomers use or most researchers use. They usually have a little bit quicker turnaround on things. Anyway. So, no one here with me. No, Clive, you would definitely not want to use that piece of information. Fursona? So, where am I going with this? Other than, again, to stroke my ego. Well, I will get there. First thing is, what is this paper? Now, because I was slow on the uptake, slow to get this published, I missed out on something. I missed out on being the first person to image star spots on a star other than the sun. That honor goes to Rachel Rotenbacher, who is really a top tier researcher, far better than I am. She did it on Zeta Andromeda, but her work is phenomenal. But technically, my data came first. I just took forever to actually publish it. And what I mean by direct imaging is if you look at any star in the night sky with any sort of telescope, Keck all the way out to Hubble, there are only two things which are resolvable. The sun, obviously, and Betelgeuse, which is a supergiant 40 light years away from us or so. 400 light years away. 40 light years? Why do I not know this? It's very close. So it's very big. Hubble is the only telescope, to my knowledge, to be able to resolve the thing, and it only partially resolved it. So you could see a disk and maybe this bright area on the side of it. Besides that, stars are pinpricks. I mean, they are so far away and so small in relation to this that that unlike what Flat Earth would say with the whole Rayleigh criterion, the Rayleigh criterion is about resolvability, not observability. If the thing is bright enough, it could be billions of light years away, and you'd still be able to see it. The light does actually travel to you, unless there is something physically removing that light from the universe. That light will get to you, and if your detector is sensitive enough, you'll see it. What the Rayleigh criterion states is there is a certain angular size based on your optical design of your telescope. There's a certain angular size that below that limit, you cannot tell any characteristics about it. For example, the classic example is two stars. If you have two stars and you are above the Rayleigh criterion, then you can separate these two stars as two stars. But as the aperture of your telescope gets smaller, the distance between these two appears to get shorter. Well, really, the stars themselves just get blobbier, but I can't do that with my fingers. But essentially, the two stars become become peanut shaped. That is when it hits the Rayleigh criterion. And then ultimately they just become one blob, and you can't actually resolve one star from the other, so you can't do any science on it. You cannot definitively say, all right, when I look at the light of this star, I am looking at component A as opposed to component B. You guys are really... I really shouldn't have said that. Anyway, I was just impressed that Tusk got it that quick. Anyway, where was I going with this? So that's the resolvability. So with a single telescope, the telescope aperture is so small, even the bigger ones, even Keck and Hubble, what have you, they're so small that the angular separation, the Rayleigh criterion, is larger, essentially, than the stars themselves. We can only see them as point sources. But we can use other techniques. And this is analogous to the dirty cheaters that are radio astronomers. They use radio interferometry to create those fabulous images of the environs around supermassive black holes. In brief, what they do is they take the light from multiple telescopes, combine it together in a certain way, that you now can synthesize the resolution of a telescope that is the size of the longest baseline. So the Event Horizon Telescope, you have telescopes on two sides of the Earth, and you combine that light together and you can synthesize a telescope that has the aperture the size of the Earth. Now we're talking. Now you can actually, your angular resolution is sufficient enough to actually image these things. Why I refer to radio astronomers as dirty cheaters is because they don't physically have to combine the light to each other. They can actually store this data onto hard drives and then basically go somewhere else, probably sunny and with Mai Tais, and put those things together. Optical and IR interferometers aren't so lucky. We literally have to combine the light on site, which drastically limits the sizes of our array. So to give you an idea, the Event Horizon Telescope, aperture of the Earth. The CHAR array, which I did this, is the size about 331 meters. So 33 times the size of Keck, the largest telescope that we have. So big from an optical standpoint, but not, super huge. Anyway, I'm digressing. Using this technique, though, synthesizing a telescope with an aperture of 331 meters, we can now start to see the surfaces of these stars. We can now start asking questions like, what are generating these star spots? Does the rotation that we infer from more indirect methods like photometric light curves, is this consistent with our understanding that difference or that variation is due to star spots? Now we can literally see this. We can literally image the surface of these stars and compare it to photometry, which is what I did. And so, oops, wrong screen. I'm not going to go into this. This is like, what is this? It's only a 19-page paper. These are all the observations I made. This is basically just proof of concept, basically saying that the observations I made do not match the expectation of a plane disk. Now, I guess this is a good segue to understanding how science and astronomy works. There's a lot of hay made about independent variables, dependent variables, all that sort of nonsense. And initially, I balked at that, particularly in my discussion with Sleeping Warrior. I was like, no, that's not how science is done. It doesn't need an independent variable and a dependent variable. Then I thought about it. I'm like, okay, with this, I can see where my independent variable and my dependent variables are, but I don't think of them that way. No astronomer thinks of them that way, because that's very rudimentary thinking. That's very basic to the idea of, yes, Clive. Let's see. Yeah, there's one. I only have like 4, maybe. I'm an observationalist. I don't do equations. Arturo's paper, which I'm going to show next, definitely has a lot more equations to it. Anyway, what astronomers do is we get observational data. We get, in this case, again, I'm really not going to get into the weeds of it, but just so we're clear, we get what is known as visibilities and closure phases. The best way to describe that is the visibility is simply the brightness of whatever source you're looking at resolved over some spatial scale, some size. Closure phase is like the contrast. What is the deviation between light? What is the deviation between two parts of the object you're looking at? Is it just a constant, just a homogeneous disk, or is it spotted? Or are there lots of spots on it? That's what the closure phase tells us. And so when we're doing this, we directly observe visibilities and closure phases. And then we use models, the hated rarefication fallacy, whatever. Because we cannot physically manipulate this. We have to rely on models. But again, consistency, which I'll show you in a minute. So when we do this, so I get a whole bunch of visibilities and closure phases. I'll come back to that. And they look something like this. These are the closure phases that I got. Where are my visibilities? Are you telling me I don't have visibilities in here? How did I publish this and not put in a visibility plot? Good Lord. Somehow okay, and they let me publish this? Anyway, so I've got this data. This visibility and closure phase data. Now I'm really curious. Just closure phase. I guess the visibility is really... Alright, I was really just more focused on the closure phases. Anyway. So yeah. So we have those two observational things that we measure. So what we do from that is we develop a model to basically... We take a model and then we figure out with this model what would be the observables from that model. So if I had a model of just a perfectly spherical disk, perfectly homogeneous disk, what are the visibilities and closure phases that I could expect from that object if I were to look at such an object with my instruments? I then take those observables, or those modeled observables, and I compare them to my actual observables, and I determine whether or not they match. If they match, then the model's good. That's an accurate picture of what we're looking at. If they don't match, then it's not. As simply as that. Now, where the independent and dependent variable comes in, I guess, and really I haven't thought too much about it, but, whatever, is I developed a model, and I did this 2 ways. I created, let's do this. I went about this in two different ways. I created a simplistic cartoon model of the object, of what I thought a Lambda Andromeda might look like, and then I used a more sophisticated, rigorous image reconstruction program, somewhat similar to what the Event Horizon Telescope folks used in order to get their snazzy pictures of the environs around black holes. The way I did this is, so with this model, there are certain components, there are certain variables that I can tweak. There is the size of the star. Hey, Blue. There is the size. Thank you for showing up. I appreciate that. I'm actually directly talking to flat earthers. It's amazing. Well, in video form. The variables for my model are the size of the star in angular size, the limb darkening, which is basically how you can kind of see it. If you go look at one of this model, it's bright in the center and then it dims over to the side. It's something called limb darkening. Again, if you're curious about the physical nature of that, I can talk to you about that offline. But it's a variable that we have to consider. Whether or not a star has significant limb darkening, or whether it does, doesn't, that affects these visibilities and closure phases. Those are the two parameters which deal with the star itself. Then you have the parameters dealing with the spots. Each spot, I can, the variables are, yes, there are a couple smiley faces in there. There is the depth of the spot or the temperature of the spot. Basically, how dark is it? The darker the spot looks, the lower the temperature relative to the unspotted surface. God, Jimbo, I really shouldn't have said that. So yeah, the darker the spot, the cooler it is relative to the surface around it. You have the size of the spot, how much the covering factor, essentially how much of the surface it's covering, and its location in the way I defined it, stellar longitude and stellar latitude. What I do, so I would keep, for instance, for the stellar size, the angular size, and the limb darkening of the star, before I even dealt with spots, I needed to find those two parameters to a sufficient accuracy, sufficient accuracy, so that I could put those aside. I could no longer treat them as independent. I can treat them as constants. And so I did that. I was going to go into, I found out that the two parameters are pretty degenerate, meaning that you can get sort of the same match of data depending on how you, depending on the limb darkening coefficient and the angular size, but I sort of digress. Anyway, I was able to get accurate values of that. And so those are my independent variables. I would change those independent variables to get me, I guess, the dependent variable, if I'm using these terms right. Again, this is not something that astronomers think of. This is not our mindset. But you change these variables, size and angular size and limb darkening coefficient, and that changes the visibilities and closure phases, or the measurements you would expect to see based on an object with those characteristics. And you compare those to what you actually see. And when those two things match up, you got your answer. When they don't, obviously you got to try harder. Once I've got that, then I can keep those fixed. And then I can start playing around with the spot parameters. I can start moving those around. I can start manipulating those around. And again, the same idea. The change in spot depth, the change in the temperature of the spot is going to affect what the visibilities and closure phases I would expect to see on the back end. Again, if I, put these, if I manipulate these things and put them together, great. The problem with the way that the flat Earth community seems to look at this is they seem to be very focused in on that you must have a single independent variable and a single dependent variable. That's not how it works, really. Other way around? Yeah. I'm sure I got them backwards, but really my point is that the whole independent-dependent variable thing is a far too rigid, it is a far too constricted idea of what the scientific methodology is. I'm hoping that I'm clearly describing in practice how astronomy is done in a scientific way. Because there are techniques, again, mathematical techniques, which math apparently is bad, but there are certain mathematical techniques such as what am I looking at? Downward simplex. There is genetic. Genetic algorithms. I'm just completely fuzzing the names. Anyway, there are ways where you can manipulate more than one variable at a time, and you can essentially start narrowing down or getting your theoretical or modeled values of visibilities and closure phases to match up with your observed visibilities and closure phases. So it's not a one, you keep everything constant and change one thing. You could do it that way. But it doesn't make much sense. It's basically you're just wasting time. Why not? If you have the capacity to look at something by changing multiple variables, then why not do that? Now, an argument could be made. Oh, well, then you don't know what the cause is. You don't know what the is the spot temperature causing the observables that you're seeing, or is it the spot location? And my answer to that is we test, the techniques that I use basically test all of these configurations. Different spot temperatures, different locations, different spot sizes, and the values that I get on the back end are the most accurate they match up best with the observables that I have. So the cause of those visibilities and closure phases is the characteristics of that spot. Now, I have done, I put together multiple spots, and it gets increasingly more complicated when you do that. And this becomes a lesson for anyone interested in doing, beyond the flat Earth community, anyone interested in doing this type of science, is that you have to be very careful with models, because so simply, what are you doing? Ron Jimbo, jeez. All right, I'm really paying attention with that. With model, particularly when you have a lot of variables you can tweak, you have to be careful on where you end that. So, for example, one of the things you can do is you can model a light curve. You can model how the light from an object changes over time. And that's a project that I have, that I'm currently trying to develop. I'll talk about that in a moment, assuming I don't keep blathering on about this. And a gentleman by the name of Jeffrey Wright was like, you can take this, you can develop a model to explain a light curve, and you can go nuts with it. If you don't check yourself, you might wreck yourself. If you don't check yourself, then basically what your model is meaningless. If you have 1,000 levers that you can throw, you can model anything. And he demonstrated it perfectly by looking. He had a light curve of Boyajian star, which I'll talk about later, which is a very peculiar star. It dims and it brightens and dims chaotically. And there were models that basically tried to reproduce this light curve And they were getting more and more complex. And so Jeff was like, whoa, we need to back off. Because what I can do is I can replicate that curve by having literally Santa Claus fly across the surface of that star. He had enough levers that he could flip, given that model, that he could match it, literally match Santa Claus going across that star to what we saw with the observations. So, as a scientist, you have to judge for yourself what is reasonable. What can you model and still reasonably expect it to be an approximation or representative of what we're seeing. MC Toon likes to basically not harps, but he stresses that science cannot prove anything or does not prove anything. And this is a prime example of this. What I'm showing you, these images that I've created, I am not saying that is what the surface of Lambda Andromeda looked like in August of 2010 and August of 2011. What I'm saying is these are the best or most probable appearances of what the star looked like on those days. Yes, Nora, that's the reason. That's the reason. Not because you are naughty or anything. So these are the most probable. Now, it's, obviously the star is more complicated than, particularly with my models, because I'm ignoring granulation, I'm ignoring any hot spots, I ignore the idea that there might be a brighter section of the star. So all of this, which I detail, I talk about all of my assumptions and all of the shortcomings of my model in this paper somewhere, and I show it. And so, getting back to the consistent. So I'm honest. I'm trying to be as intellectually honest as I can, and say this is what I got. These are the assumptions I made to get here. These are the things that I did not account for. But given all of that, this is what I believe is the closest that we're going to get with this data to what Lambda Andromeda, the surface of Lambda Andromeda, looked like in August of 2010 and August of 2011. Now let's get back to the idea of two disparate methods getting the same conclusions. So the method that I was talking about before was my model. It was literally a cartoon model. I just put spots on a disk and went nuts with it. I limited it, kind of finishing off that last thought, I limited it in that I did not model anything greater than 4 spots. There was really there was nothing in the literature, there's nothing that would physically motivate me to believe that there are more than potentially 4 spots on the surface of this star. Again, for reasons which are beyond the scope of this. So this is my cartoon model. The middle row uses a completely different method, which again is far too complicated for me to get into in this discussion. But basically, what it is it assumes it starts off with a disk. It starts off with some prior. It starts off with whatever you like. I used a disk because if you use a point, things get messy and it takes far longer. But if you start with a disk, something that looks approximately like what you expect it to be, and then it will use a Markov chain, MCMC, where it will just constantly randomly move flux around, and that generates indivisibilities and closure phases, and that gets matched up to the observables. Can you yodel? I don't think you really want me to. Yes, but I don't think you really want to hear it. So it uses, instead of strictly defining spots, circular spots on these stars, it basically just moves the flux around. It just moves the brightness around however it likes. And it can create bright spots, as you can see. It can create dark spots. And so there are certain limitations to this method, but it is disparate. It is independent of the method that I used with the model. And so when we look at this, again, it's not perfect. It's not there are problems with it, which I freely admit and can explain. But it is very hard to explain why there is a spot here in my model, and then a completely different method gives me a spot in pretty much the exact same location. We also see these spots collected here in a line. We see them there. You can see that there is rough agreement with the dark spots. Now the light spots, that has to do with the limitations of the reconstruction, the image reconstruction. The regularizer, basically how it regulates where it's putting the flux, was not sufficiently sophisticated at the time. And so this one down here is basically a simulated image using a friend of mine's code, which again uses a completely different methodology. But it was really, the focus of this paper was really to compare my model, my cartoon model, to the image reconstruction program. And to me, because maybe I'm biased, but there is consistency between these two. And that is the cornerstone of astronomy, and really the cornerstone of science, is you have to have if you make an observation and you make a claim, I make a claim that on August 18th, August 19th, this is what Lambda Andromeda looked like, at least the first order. Great. I make that claim. Then that has to be verified. Typically that is done by other people, but I can help verify it by using a completely different method to get to something that is very similar. And if there is, do you do the rest of this in the style of Slim Whitman? I actually don't know who Slim Whitman is. But these two things are consistent with each other. There is consistency between them. And so, again, we can look at it. And I can go a step further. A gentleman by the name of Dr. Greg Henry has been studying the star for ad nauseum photometrically. Basically, he's looked at the star's brightness over time, and he got something, and this is the typical way, and he gave me this data, for the use of this project, for basically the amount of time, or the span of observations that correlated with mine. They weren't simultaneous, but they were contemporaneous. They were basically close enough in time. This also is another hallmark of science. Science is not done individually. If you are the only author on a paper, chances are you are a quack. Science is collaborative. We work with other people. The primary reason we work with other people, well, there are two primary reasons in my opinion. One, divide the labor. You have this is a depending on the science you're doing, it can be rather involved. And so if you can, I can't think of the word, if you can push off some of that work onto other people, fantastic. The other thing, though, and this I think is the most important, is, and this is what I did with a number of the papers that I'm published on, is I provide, or they provide, a check. You do, hey Demon Orb, they do if one of my authors or one of the PIs on this, or principal investigators, they basically make the claim that, okay, Santa is literally flying across this star. I would then go to him and be like, really? You really think that's physically possible? I mean, he's not traveling at the speed of light, and we all know that he has to be traveling greater than the speed of light in order to deliver all those presents. So obviously that can't be Santa. Maybe we should look at something else. And so the authors of the Orion Seance, the authors basically allow not only divvy up the work, although the first author is stuck with actually writing the damn thing. they divvy up the work and they collaborate they collaborate data. They basically allow data to be used. In this case, Dr. Henry allowed me to use his photometric data, but they also provided check. So I was able to phase this up, and so basically I had observations detailing basically 4 seasons. These lines here indicate the specific times of my interferometric observations. Now what I can do with this is, if we go back to this, I can basically say, I can say what the light curve would look like. So I basically can say, all right, the amount of light that I would get from just a limb darkened disk with nothing on it is this. If I put spots on it, I can basically say that the amount of light that I get from that is this. And so what I can then do is compare it to the light curve, the photometric light curve. Yes, there is a disparate point. I will freely admit that this is a first paper. This is like I said, this is the first time really anyone had ever done this. So yeah, it's going to be a little bit crude. But this is 1.6. You can see that I have overlaid the magnitude, the change in magnitude of my image, of my models, over the actual photometric data, and it matches pretty well, which again provides yet another check, yet another piece of consistency that provides evidence to give me confidence that what I'm doing is right. And I think I'm just going to leave off on that paper because, yeah. Now, continue on with the consistency, and this is way cool. This was done by Arturo Martinez. He was the grad student of my old postdoc advisor, and his work is fantastic. He took my data and used updated techniques. What I did was I basically modeled these things, or imaged these things, in a snapshot sort of way. So I had data corresponding to the 18th, 19th. I had data corresponding to the 24th, 25th. Basically 6 different epochs. And I modeled them independently of one another. What Arturo did was he used updated software. And he was able to come up with this, which, here you go. These are visibilities. These are he makes much prettier plots than I do. I didn't think of actually putting rainbow colors in there. Anyway, so these are the visibilities. These are the closure phases. So those are the actual observables. More of those. Here you go, Clive. This is he used rotor, or the rotational image reconstruction program. And here is all of the nitty-gritty equations that go into how this thing does it. Here's an equation for differential rotation. The differential rotation, which is a thing. And then here are some of the examples of the reconstructions. Now, I mentioned before there is this thing called a regularizer. Basically, how well or how limited is the program able to, or how freely is the program able to distribute flux willy-nilly. If you have a very weak regularizer, then it's going to overfit the data. You have an incomplete picture. The data is incomplete. You do not have data over the entire star. You only have data for certain sections of it. And so it will overfit that. It will put too much emphasis on the data that you have and pretty much just give you an unphysical picture of everything else. That's on the left. If you over-regularize it, if you really constrict, or if you really constrain where that flux can go, you can then basically underfit the data, and you come up with something that really looks completely unphysical. It basically is it is forcing it to look like your prior, more like your prior than your actual data. But there's a sweet spot that you get in here. And again, these are all done. We distinguish them not by eye, not by subjectively saying, hey, that one looks cool and that one doesn't, whatever. Or we don't call up, Jim Bob from the other office and come and have him say, which one does look good to you? We don't do that. We have statistical methods that allow us to determine the quality of fit. How well does this image fit the data that we collected? And we can then pick the right parameterization to use this. And then he got this. I know you're probably not amazed with this, and actually the color is a little bit weird, but yeah, this is, I could look at this all day. What he did was, instead of imaging these these epochs, these observations on 6 separate days, he modeled it as a whole. He modeled it as an ensemble. And so again, even more consistency. I'm going to hammer this home. Even more consistency. Hey, Jeff, thanks for showing. I appreciate you. Even more consistency, because the data basically worked as a whole. And so if any part of the data didn't agree, it was basically going to shoot down the entire model. All of the data had to give you a coherent picture of what the star looked like. Now, why does it look so ovular? That's simply that's projection of a sphere onto a 2D surface. I can't remember which. It's right there. A Maude-Weidel plot. I have no idea what that means. So that's just the type of projection to get it on there. And so you have these spots. Basically, you can see what the surface of this star looks like in that span. You can see all the dark spots on that surface. And down here, you get to see the spots as they are from individual epochs. And for me, there are pretty, if you look down here, compare those to these three, there is consistency between his method, which again uses a different technique, and my method. And so again, here you have that string of spots across the midplane. That string of spots across the midplane. Same data, different techniques, same result, or comparatively same result. Why does this happen in a flat Earth model? If space is junk, if space is not a thing, if it's all just a light show in the sky, why is it that we can use these techniques, disparate techniques, look at these objects and get the same answer? What sense does that make? Like, why would the universe behave in that way? It doesn't make any sense to me. It doesn't make any sense to me. Why this is the case? So if you're going to assert that the Earth is flat and that the sky is covered in a dome and these are simply luminaries, then you're going to need to explain to me why it is that all of this stuff makes sense. It builds on top of each other. So, all right. So let's move on to some other stuff. So that's basically, so just to summarize, what I did was, all right. So I looked up, I knew that Lambda Andromeda showed photometric variations. It got brighter, it got dimmer over time. I then looked up all of the research that I could find about Lambda Andromeda, and I wrote it all down here. That is the background research. I then came up with an observing strategy, or then I came up with a hypothesis. It basically said that these observations that have been previously identified and previously identified as star spots, I agree with that. I believe that they are star spots, but I'm going to show that I can provide a better estimate of what these spots look like. And so I came up with an observing strategy. And I have interferometric observations, I have photometric observations, yada yada. I did that, I came up with that strategy, I performed an experiment. I then used that experiment to test my hypothesis, basically to see whether or not the quality of fit between my guess, the model that I'm using, and the answer that I have based on the directly physical observations. And I compare those two, and I test and see what I get. And I get that my hypothesis was confirmed. These observations more than likely, or most probably, caused by star spots. There is really no other mechanism that would give us the observations that we have. With the reconstructions, the model, again, there are some limitations. I limited the number of spots to 4. I didn't put any bright spots on the thing. Small scale structure, I didn't worry about that. But the other methods, the other reconstructions that were done, didn't have those limitations. They could put bright spots on there or not. So these spots are the best approximation that we can get. These are what we refer to as direct images. These are blurry images. While these things are resolved, they're not resolved a lot. Lambda and drum, to give you an idea, a resolution element, or the smallest area that you can resolve anything with, you can put 4 resolution elements across lambda and drum. So it's very, very crude. So a lot of this smaller scale structure you probably going to want to squint at. But the larger spots, good. So yeah, I saw saw a phenomenon. I researched the hell out of it. I came up with a strategy to determine whether or not my hypothesis of star spots would actually work out. I then tested that and came to the conclusion that yes, star spots are responsible for the observations that we see. And then Artur came along and basically said, yes, I agree with Rob. He is awesome. All hail Dr. Rob. Well, he probably didn't say that last part, but, yeah. Oh, the other thing is, thank you, Jezza, for putting this in there, is we also get, I also get that we're all NASA shills and all that kind of good stuff. Well, at the end of the paper, we are required, encouraged probably, heavily encouraged, highly encouraged, to tell you where all our money came from. So this work was funded by ESA. It was funded by the Gaia Consortium. It was funded by the National Science Foundation. And yeah, no NASA. NASA gave me no money. No money from NASA for this project. So, there you go. Let's see. Arturo, let's see. Where did you get your money from? And yeah, we do this. We basically have to, we disclose where we get our funding from so that we don't get accused of any sort of misdealings or conflict of interest and all that kind of good stuff. So Arturo got his from National Science Foundation, 2 grants, and maybe a couple more grants up here. But yeah, no NASA. NASA did not fund this at all. The government did because it's a National Science Foundation, but NASA was not a part of this. All right. Let's see here. All right. I don't know if I want to get into all of these. This is something that's very near and dear to my heart. This is the first paper that I worked on. I actually took data on it and reduced it. This was a pain in the cojones, because what we're trying to do is we're trying to find the distance and membership of an open cluster, basically a conglomeration of maybe a few hundred stars. And just very briefly, what I did, my contribution to this is the way that we can, in brief, the way that we can determine the distance is by figuring out what the brightness of all the stars in that cluster are, and then we can go from there. It's basically spectroscopic parallax. Again, if you'd like to know more, click here. No, sorry, that's Starship Troopers. If you'd like to know more, then please see my lecture, 113 lecture on taking the measure of stars. Spectroscopic parallax is in there somewhere. But this is what I am really, really proud of, because this was a pain in the... I did absolute photometry. Now, so what is it? All of these points, all of this data, that's all me. I was the one who determined all of that. And I did absolute photometry, which I can't express to you how difficult that is, particularly in the really crappy environment that I was in. The fact that I could do this at all, I should be given a medal. Maybe not a Nobel Prize, but I should be given something. It is damn difficult to do this. Mostly we use differential photometry. We look at the brightness of one object with respect to the other, another object in the field. Absolute photometry is a way to basically say that star has that brightness and full stop. It's not in comparison to any other stars in that field. That is its brightness. It's very difficult to do. Google it if you'd like to know more about it. So I did that. And I'm very proud of this paper because, like I said, it is, I think, the first paper that I was ever authored on. And I am the third author on it. This one I like because it shows that I'm just a versatile dude. This, again, is most of my contribution from... respect. Yes. Yes, Carl. Your respect, damn well appreciated. I do appreciate that. Thank you. Absolute photometry. This star has that brightness relative to others. That's differential photometry. That's where basically you say that this star is twice as bright as that star. Absolute photometry, that star is fifth magnitude. Full stop. It's not 50 times brighter than the other star. It's not relative to anything. So, I did some observations on using, again, I think in this case, a 24-inch telescope. I looked at an active galaxy known as a Seaford galaxy with the romantic name of UGC blah 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 license plate number. Now, what's seriously cool about this, at least to me, is that, again, if you can do something in science that is direct, that is, you're not making a whole lot of assumptions, you're not going from point A to point B to point C to get to point D. If you can go from point A to point B and that's your answer, fantastic. It is the best science that I know how to do. Best science that I know out there. So this is, you've seen those images. Hopefully you've seen those images of the supermassive black holes. But before all that, we were able to directly determine the mass of a supermassive black hole in the centers of galaxies that were millions of light years away. And I contributed to that effort. Dr. Misty Bentz, fantastic woman, fantastic scientist, she spearheaded this. And again, simply put, what we have is you have a black hole, a supermassive black hole in the center of this galaxy, of this massive galaxy. And we're talking about a black hole. This environment we're talking about is basically the size of of the solar system. So that small in comparison to a ginormous galaxy in technical term. That supermassive black hole region, so you have the supermassive black hole at the center, which is not producing any radiation at all. Surrounding that, you have this accretion disk of material, this thin disk of material which is rapidly revolving around that black hole and is feeding it. That material is being dumped into the black hole, never to be seen again. And because of the shearing of the material that's happening in that disk, it radiates energy, and it radiates a tremendous amount of energy. Beyond that, you have this cloud or this torus of material. These are basically just clouds of gas and dust that are moving very, very rapidly around this whole thing. This technique is referred to as reverberation mapping. What we do, or the underlying physics, is that the accretion disk burps. More specifically, the rate of accretion of material onto the supermassive black hole is not constant. It is chaotic, and occasionally you will get a point where a lot of material will get backed up. It'll create basically a burst of energy, and that energy propagates through or reverberates through the disk, and ultimately goes out into the broadline region, that big torus of gas. So what we do is we use optical interferometry, or we use optical photometry, basically in blue color, green color, red color. And we look at the photometric variations of the object over a span of time. And then we compare that to simultaneous observations done spectroscopically that are looking at hydrogen specifically, in this case, hydrogen beta. It's a very specific transition of hydrogen. And that is located in the broadline region, in that torus. Now, what we would expect is that there is going to be a delay because this reverberation has to travel at the speed of light. There is a delay. There is a certain amount of time it takes to move through that disk and get into that broadline region. And what we're doing, what I helped contribute to, is I measured the BV&R data, the BV&R brightness of this thing. And we compared that to the spectroscopic data that we got from Apache Point. Again, the photometric data here was taken at Hard Labor Creek Observatory in Georgia. 24-inch telescope, fantastic plane wave. Oh, love that scope. Probably my favorite scope to ever use. All right, so yeah, once you get that data, once you get that time lag, basically the time it takes for that burp to get to the photometric wavelengths, which basically means a certain what's the word I'm looking for? Distance within the disk. If it's very close to the black hole, the energy is going to be in the X-rays, or very, very high energy. As it moves away from the disk, the energy is going to become ultraviolet, which is still high energy, but not as high. Then it's going to the visible, and then into the infrared, and ultimately into the radio. And so as that reverberation goes through, it's going to eventually peak in the in the visible. We measure that. We see, all right, there's a spike here at this time. It then moves into the torus, and then the observations from Apache Point, which is a 2-meter telescope, which uses spectroscopy. Again, getting into the weeds. They again measure essentially that blip when it hits there, and so you can then get the radius of the broadline region. You can get the radius of essentially the disk of this black hole. You can also get, based on the let's just say, based on the spectroscopic measurements, because the Doppler effect is a thing, you can determine the velocity of the disk surrounding this supermassive black hole. And because gravity is a thing, the more massive something is, the faster it's going to cause something to spin around it. Because gravity, again in the classical sense, the force of gravity is equal to an acceleration. The higher the mass, the larger the force, the greater the acceleration. So, bing, bang, boom. And then to appease Clive, Clive, you have this equation, very simple equation, really, and I love this about science. Some of the most powerful equations are some of the simplest. F equals ma, E equals mc squared, V equals IR. I know I'm going to get screw that up. And here we have the mass of the black hole is equal to F, which is literally F fudge factor, times the speed of light, times the time delay that we can measure, times the velocity that we can also measure from the spectroscopy, squared, divided by the gravitational constant. That gives us the mass of a massive black hole. We are able to directly, by determining the velocity of how fast stuff is spinning around this black hole and how big this disk is, we get the mass of something that is millions of light years away. Mind-boggling to me. Now, again, consistency. How do we have any clue as to whether or not this is real? And in this case, this supermassive black hole is actually kind of teeny. It's around 7.1 plus or minus, because error bars are crucial, 7.1 plus or minus 4 times 10 to the 5th solar masses. So we're talking about something that is, 710,000 times the mass of the sun, which really is teeny when it comes to supermassive black holes. Typically, they're on the order of millions or even billions of times the mass of the sun. So, consistency. This is not the only study that's been done, and it's certainly not the only study that's been done by Dr. Bentz. A lot of these have been done, and so we can see that we can see that there is a relationship. And for galactic work, this is a very tight relationship. It's kind of an inside joke. Stellar astronomers, we get these nice, well-fit lines. Galactic astronomers, not so much. They basically have to put it on a log plot in order to actually make it look reasonable. Anyway, funny to me, probably not funny to anybody else. But we can see that when we look at the size of the disk, and we compare that to the time delay, we get a very nice linear relationship between those two. Actually, exponential relationship, because this is log. And it fits right along with everything else, with everybody else. And these are different objects. While it's the same technique, it's reverberation mapping, now it's different objects. So the same physics is happening with UGC license plate number. It's also happening with other AGN. It's consistent. It follows from one to the other. The same technique gives us a consistent relationship between these two, and that also then can be used to determine things like what is the mass of the supermassive black hole with respect to the velocity dispersion of the stars in that black hole, or in that galaxy. The velocity dispersion, essentially, what is the average velocity of all the stars swimming around in this galaxy? You would expect, well, actually, this is really one of the questions that they're asking is, which came first, the supermassive black hole or the galaxy? Did the supermassive black hole provide the gravitational potential well that all of the stars kind of coalesced into? Or was the galaxy have a much larger gravitational potential and kind of settled that way, and then stars in the inner part basically went supernova and slammed into each other and basically created these supermassive black holes. So one of the ways we're looking at this is we want to know whether or not there is a relationship between supermassive black hole size and the velocity dispersion. This tells, if there is one, then that leads us to believe that the supermassive black holes came first. That the mass located there is what sets up the gravitational potential, and that dictates the speeds of things in that potential. Again, pretty consistent. There is a relationship between the mass of the black hole, supermassive black hole, and the velocity dispersion. Again, gravity is a thing. The larger the mass, the higher the amount of gravity, the faster things go. And that's what this is showing. The higher the mass of the black hole, the faster things are going. It's beautiful. It's just, I love how science works. And thank you guys for listening to me geek out on this. I love this stuff. And then also, on top of that, we get a bonus. We know the mass of the supermassive black hole, yet another simple, beautiful equation. The radius of, I think, is this the Schwarzschild? I want to say this is the Schwarzschild radius. The point of no return, the radius of basically the intrinsic size, as it were, of this black hole is equal to the gravitational constant times the mass of the black hole divided by the dispersion of the stars squared. Sphere of insolence. It's not the Schwarzschild radius. It's the sphere of influence. We can get that. Basically, it's a characteristic size of. So not only do we have the mass, we also know ultimately how close you can get to the sucker before you get spaghettified and go nowhere and get tossed around and stuff. Anyway, let's see. So yeah, I love this because my area of expertise is in stars, really. And so I was gifted with this opportunity to work with Dr. Benz, work with Misty, on expanding my my horizons, as it were. I am, from another way of looking at it, I am a photometrist. I primarily deal with data that tells me how bright things are over time. And I am an interferometrist. I also dealt with using an optical interferometry to get high resolution images of other objects. Normally, I use photometry to look at stars and stuff like that. But Misty gave me the opportunity to use those same techniques to look at a friggin' black hole. I'm like, yeah. She asked me, you want to work with this? I'm like, hell yes. Yes, I want to look at black holes. So I, basically took some time off my dissertation to work on this. I was like, I could take a little break. No problem. I don't know if my advisor really liked that idea, but anyway, there's more to this paper. Obviously, this paper is long. Now, the last thing I want to talk about is, let me do this real quick. Nope, over here. Is this the other part of my dissertation? The thing that I love, that I really get a kick out of, is oh wow, what is this doing? Stop doing that. Come over here. All right, there we go. That's better. I apologize. This is a PowerPoint slide being put into LibreOffice, and so obviously you're going to have compatibility issues. But anyway, what is a young stellar object? A young stellar object is a protostar. It is essentially what if the thing is before it becomes a star. It starts out as a large prenatal cloud with denser parts of it in. because gravity is a thing, it causes those parts of enhanced density or places of more compact mass has a higher gravitational effect. It brings the stuff in. And that reduces down to a protostar, basically a central, very hot mass, typically on the order of 3 times the size of the sun. And then you get this nice accretion disk around it. That's another thing that's awesome about these things. Young stellar objects, black holes, white dwarf, or I guess novae would be the better one. All of these things have very similar characteristics. Disks, which form because of rapid collapse, or reasonably rapid collapse, of a thing, conservation of angular momentum. It's just beautiful how these physical concepts, we see them in young stellar objects, protostars. We see them in black holes. We see them in the formation of novae. These are wildly different phenomena. They are not related to each other in any way, except for the underlying physics. The underlying physics dictates what we're seeing. It dictates the formation of accretion disks, so forth and like that. But getting to where I'm going, these young stars, or these YSOs, go through various classes. And so you have class 0, which basically corresponds to, I guess it would be this here, where you have a protostar which is heavily embedded in dust and gas. Barely even see it. It's a very chaotic environment. Things are causing variability all over the place. This thing is, if you looked at it visibly, or if you looked at it photometrically, this thing is going to go nuts. When the cloud collapses, most of that dust and gas is going to be constrained to the disk, and so you get a better view. It's no longer as enveloped, or enshrined. Anyway. So now, it's still going to be variable, but its chaotic nature is not going to be as much as with class 0s. So these are class 1s. And then class 2s, the disk gets further diminished. In class 3s, you get into debris disks. That's when the planets have formed, yada yada. Why am I bringing this up? Because of this paper that I wrote. This thing was a beast, or is a beast. Nope. Where are you? Nope. No, I have you. There it is. This paper is 40 pages long. Granted, there's a lot of figures, but 40 pages long. Most papers are like 10 to 20. A lot of work went into this. So what I did was I looked at a region of space. I use archival data for this. I didn't actually do the observing. Some other people did the observing, and I just took their data and did other stuff with it. And what I did was I looked at this field, this thin strip of sky, and which had approximately, I want to say, 1,700 stars. So I looked at the photometry for roughly 1,750 stars. So a lot of stars is what I'm trying to get to. I looked at all these stars. I looked at the photometry, and I was trying to figure out, all right, well, the first question is, are they variable? If I'm going to try to piece out the question I want to ask, again, trying to go back to this scientific notation, or scientific method, is I observe, or YSOs have been observed to be variable. My question is, okay, what causes that variability? What is the physical mechanism for why these things vary? So I did a whole bunch of research on YSOs. I said, yay, this is what we'd expect. And then I took these observations and created an experiment, as it were. Well, the first thing I needed to do was to figure out what whether or not they're variable, or whether or not these stars are variable. So what I can say is that a variable object is more than likely going to be a YSO. Now, there might be YSOs in there that I don't detect as variable for one reason or another. They just aren't variable. That can happen. Rarely, but it can happen. But the ones that are variable, more than likely, good chance, those are going to be YSOs. Those are going to be variable. And so, oh look, more equations. Let's see. This is basically stack this on top of this, and you get this. So I don't want to bore people with this. I know I'm excited about it, but what have you. And what I found was I came up with 4 criteria, 4 physical mechanisms that would explain these things. Cool star spots, long-lived. We're talking on the order of weeks to months. Long-lived star spots that are rotationally moving around. And what I would, based on the physics of that, I would expect the periodicity would be periodic, the variability would be periodic, and within a certain range. Young stars typically have rotation speeds around 14 days or less. Think about that. A star that is 3 times the mass of the sun is rotating once every week to 2 weeks. If you don't find that fascinating, I don't know what to tell you. So cool stars, it would have a certain rotation rate or a certain rotational period, and it would be colorless. Basically, it wouldn't be red as it rotated. It wouldn't be red. It wouldn't be blue. And then, are you guys still out there? I haven't seen the chat update in this in a while, but I guess I'll just keep going. But I won't belabor this. I came up with 4 criteria. Long-lived cool star spots, variability due to hot star spots, variable extinction due to dust, which can either be periodic or long time scale, and then variability due to accretion. Each of these has certain observational signatures, and that's what I'm testing for, and that's what I'm looking for. And so I went through this, and I found these variables, and I found about 101 variables out of this 1,700 survey. And the first thing I did was I looked for periodicity. I ran this thing through a novel period finding algorithm, which is detailed in all of its glory up in this region right around here. And I found that there are about, some of these were actually periodic. And you can see that these are basically phased. You take all of the data, which spans through. Oh, I should mention, this study is as far as I know, the only one of its kind because of certain constraints. So when it comes to YSO variability, most studies so far basically are either hot, or the studies can be 2 things. They can either be high cadence, meaning that the span of time between individual observations is short, or they can be longitudinal, largely longitudinal, meaning that the span of observations can last years. It can be one or the other. This study combined both. I have approximately 3 years worth of data with a cadence of about 1 day, which you'll have to trust me, that's pretty high cadence. And so that allowed me to look at these YSOs in a way no one else had been able to. And so I took this data, I could phase it up, and this is periodic with a phase, with a period of 14.52 plus or minus 0.088 days. Error bars. Every piece of data must have error bars in order to be even considered to be viable. Because again, science doesn't prove anything. Science only gives confidence. The size of your error bars are your indication of how confident you are. Because the error bar is so small, I am very confident that this thing is varying with a period of around 14 and a half days. And then you get these other ones here. Now, I go through this, and I go through these various light curves, and I phase them. Then I basically match them up to my criteria to see whether or not my observable criteria to see whether or not I can make an estimate or say anything about what the variability mechanism is. And so let me give you an example. Actually, let's go all the way down. Oh, this is an interesting one. I really wish I could go back to this one. This has the characteristic curve, photometric curve, of a pulsating variable, probably an RR Lyra, meaning that it's a very young, very low mass pulsating variable. Well, I should say low mass, not young. It is a very low mass pulsating variable, so it's not a YSO. But what's weird is this little thing. Pulsating variables in this range, in these wavelengths, should be colorless. When it gets larger, when it gets smaller, it shouldn't get bluer or redder in the infrared. For some reason, during this transition, when it gets brighter, so it gets smaller, when it rises and gets smaller, it gets bluer. No idea why. It's one of the many things I wanted to go back after this paper was done. It's one of the many things that I wanted to kind of go back to, but I never got the chance to. Oh, look, another equation. So that was a cool thing. Not a YSO, but still kind of freaky. The cool one is, let's see. Let's get down to the nicey ones. There were 6 that I highlighted. All right, let's start with this. Let's start with these two. These are what I refer to as long time variables. They're not periodic, or at least not periodic on a span of 3 years, but they do show definitive variability. The brightness is not constant over time. So let's look at this area right here, the third epoch, or basically the third year. What I can say is, and I can also say it for this, if the brightness is changing because there is dust in the way, or extinction, there's dust basically blocking the light, we would expect the light to become redder in that case. And that's exactly what we see here. As the light diminishes in K, one particular filter, when we look at the colors of, in a way, basically J minus H and K, H minus K, really just colors, we notice that as the light diminishes, the amount of light diminishes, the color of the object gets redder as we see it. So I have confidence. This is a little bit more subjective because I could not figure out a way to quantify this. It's one of the things that really kind of stuck in my craw about this study, is I could not figure out a way to quantify this. It was really kind of subjective, at least this portion of it. But it got redder, so that indicates that it's extinction. Extinction probably doesn't necessarily have to, or I should say, doesn't necessarily have to be periodic. Probably is, but that's if the dust is far enough away from the star, the periodicity can be far longer than 3 years. So it could be that if I looked at the star for 10 years with the same cadence, I would see something like this repeat over itself. Now this star, I love this star. This star is extremely bright, and the spread in the photometry is so small. You can see that a lot of these things, the photometry is really all over the place. These are just chaotic as shit. There's just variability. It's basically variability mechanism on top of variability mechanism. And so it's very hard to really piece out what is the dominant source. With this one, nope. It is clear as day. We have the photometry. It has a very steep drop in the K. The light diminishes incredibly, and it gets bluer. It gets noticeably bluer. There is no distinction. If If the points go up, that means that the star is redder. If the points go down, that means the star is bluer. This is a perfect illustration of accretion. What I was talking about with the black hole, with the disk, that material in the black hole was falling into that black hole, and the disk was, and that causes the disk to glow. It basically creates energy. Same thing happens around a protostar, is that you have this disk surrounding that protostar. It's feeding, the material's feeding onto the protostar. It is not constant, and so things can get backed up, things can get brighter. The spot, unlike a black hole, what's happening here is that the point at which that material slams into the star causes it to be really, really bright in that little location. And what we're seeing here is as the thing gets dimmer, it gets bluer. Essentially, that creates a large spot, and it basically just diminishes the entire star, and it gets bluer in the process. And it's doing so on timescales of years, which had never been seen before. A lot of this had never been seen before, because a lot of this had never, the time span, the temporal baseline, as I like to say, has never been long enough to see these kind of fascinating features, to understand that these variability mechanisms not only exist, but they can exist on very long timescales, at least from a terrestrial point of view. And the last thing I will say about this is, and I don't really, where did it go? Oh, this one. Yeah. Love me. Is it this one? Where are you? My favorite. Where's my favorite? Can't believe I can't find it. I think it's YL. YLW1C. Yeah, it's this one. So what's fascinating, and I can't seem to find. Let's see if I can find. Right, YLW1C. That's the periodicity. That's the eclipse periodicity, and it's also a sinusoidal variability. There it is. There we go. So what we're seeing with this particular star is, with a lot of these stars, what I can do is, for the vast majority of them, I really can only tell you what the dominant variability mechanism is. As I said, these are very chaotic. They have variability mechanisms on top of variability mechanisms. The scatter that you see in this curve is due to the fact that there is something else happening causing the star to change in brightness over time. Very rarely, I was able to actually distinguish two different variability mechanisms. This sinusoidal variability told me that, again, it was colorless. This told me that there was a dark spot going around the star, causing it to vary in a sinusoidal way. But I also noticed that when I did, and I phased it up, and the period of this is 5.7752 plus or minus 0.0085. Very, very certain about this periodicity, about this sinusoidal sine wave. So what that's telling me is that the star itself is rotating. Again, this is a star roughly 3 times the size of the Earth, or 3 times the size of the Sun, rotating once every 6 days. The Sun rotates once every month for a scale. So we got this. But I also noticed, wait a minute, what is this? There's a whole bunch of junk there that really wasn't fitting. So I went back to my periodogram, and I was like, well, what if I put it in a different period? What if I phase this up differently? And then I got that. And so this garbage here on the baseline, that is due to the sinusoidal variability. But then if I phase this up to a period of 5.95, so the other one was 5.77, this is 5.95. Again, the error bar is very small, so I'm very confident about this period. We get this nice eclipse feature, which is red, which means that it is caused by extinction. the most plausible explanation for this is that we are looking at something which is caused by the formation of a hot Jupiter. A hot Jupiter is a Jupiter mass planet that is very, very close to its host star. And so that sinusoidal variation that we're seeing is because there is a spot rotating around. This eclipse feature is because there is a clump, a larger clump of the disk. The disk is not flat, perfectly flat. There are clumps in it. There's a very large clump, very close to the star. Now, the clump is more than likely not the forming planet. The clump is more than likely the planet being a bully and just forcing all that material into that localized area. I actually did a little bit of back of the envelope calculations, and it really doesn't make sense that it's actually the protoplanet. I was really hoping that I found actually a protoplanet, but no. What I found was the indication or evidence that there was a protoplanet throwing its weight around, literally throwing its weight around, causing that to do its thing. So, why is this study? Why is it sort of unique? Granted, I haven't looked at the literature in a few years, so maybe someone has redone this. But the last bit of research that I've seen on this has been extensive studies, very high, having higher cadence than a single day, over a span of about 40 days. And they can see a lot of different interesting features with the variability of YSOs. The reason for this is astronomy is very competitive in terms of resources. You know, with a physicist, basically you go in a lab, and I'm intentionally trivializing this. You go in a lab, you buy your equipment, no problem. You set it up, you do what you want to do. With astronomers, in order to get this data, there are only a set amount of telescopes that we can use. And everyone wants a crack at it. Everyone wants some time on it. So this type of project is what we refer to as observationally expensive. It requires a lot of time on any particular telescope. Now, what TACs, or telescope allocation committees, do is they want to be as fair as possible. They want to get as many projects the opportunity to get data as possible. And so what that means is that they will more than likely shorten the amount of time that you ask for. So you might ask for a month's worth of time, they'll give you 2 weeks, so that they can bring in somebody else and allow them to do a project. So with research-grade telescopes, this type of project cannot be done, because you cannot ask for this amount of time with this cadence on any sort of research telescope. No one is going to give you that much time devoted to a single project. And I agree, that is selfish and shouldn't be done. The reason why I got this data was because it was part of a different research project. This is archival data. It was used for a different reason, and I was able to put it to use in a different way. So, where does this bring me? This brings me to what I would like to do in the future. So looking at these stars is very difficult because they are embedded within this dark cloud, or in this cloud full of dust. To give you an idea, the light diminishes by a factor of 24 magnitudes. So let me put it this way. Imagine you're looking at the sun in the sky. Then you take a whole bunch of dust, basically put it in between us. The sun essentially disappears, completely disappears. All of that light gets blocked out by that dust. There's no real way to penetrate. You could really only penetrate it using infrared wavelengths, which again, whatever. Which again, I have lectures that go into that in a little bit more detail. We can only do this with infrared. Now, infrared is tricky because it really can't be done from basically the ground because of humidity. You either have to be in space, in the sky. Oh, Sophia, somebody literally put a telescope on a jetliner. Nuts! And it works. Anyway, that's awesome. I really wish I could fly on Sophia and use that telescope. Anyway, so you either you're limited to space, you're limited to air, that one particular airliner, or you're limited to a high mountain. But there are, I have found, YSOs, and in this case, I do actually have to thank the Russians. The Russians did a group of Russians looked at YSOs, a group of YSOs, over a long time frame, but their cadence wasn't great. And these are what we refer to as sort of what I refer to as naked YSOs. These are YSOs that are forming, and for whatever reason, the enveloping cloud has been dissipated. And so we can see them. The amount of extinction on these stars is not nearly as great as we see in this particular sample. And so what I would like to do is I would like to use the telescope that we have here, and I would like to look at these roughly around 30 YSOs with our telescope with a very high cadence. I'm talking, instead of a day, I'm talking about minutes or possibly hours. I have to compete with exoplanet work here, but as small a time limit as I can, and I'd like to look at them for years. And when I do that, I think I will not only be able to sample what the variability looks like on very long time scales, like I showed you with that one particular accretion thing, but also no one has really studied what you can call micro variability of these things on hourly time scales. And that being able to get those observations would lead us possibly to understanding that we don't fully understand all the variability mechanisms that are present. I only listed 4. That is definitively not a complete list. There are other things that are going on causing this thing to vary. Pulsations, flares, you name it. So getting that data will allow us to sample a region of these YSOs that no one has ever looked at before. And the reason why I can do that is because I am not at a research telescope. I am at a university telescope. So all I have to do is I have to compete with my boss, who likes to look at YSO or likes to look at exoplanet candidates. And he has already told me that if I come to him with a project, he will give me as much time as is reasonable. So that is what I'm going to do, and I'm hoping to be able to maybe get a student or two interested in it. I'll take the observations. These will be an optical, so it's not quite the same, but really what I'm going to be doing is I'm going to be looking at these stars, determining their rotation rates, and the best thing I can do, or the thing I can think of to do now, is see whether or not those rotation rates are slowing over time due to magnetic braking, but that goes way on. Again, I can go on for a couple more hours just talking about that alone. But, so, bringing everything back full circle, because again, this talk, or this stream, is really directed towards the Flat Earth community. And I would appreciate if you know a Flat Earther, send them this way to it. They'll probably zone out most of the way through it, but hopefully in the beginning and hopefully at the end if they stay. I will then, again, ask you. I have defined how we do this. I have hopefully illustrated that I do use a scientific method. I see a phenomenon, I research that phenomenon, I come up with a strategy in order to explain that phenomenon. Basically, I come up with I research the hell out of that phenomenon, I come up with a hypothesis to explain that phenomenon, I develop an observational technique or strategy to test that hypothesis, and then I go from there. I see whether or not the hypothesis is correct. If it's not, I try to explain why my experiment failed or why my observations failed, so forth and so on. So I do use, astronomers do use the what I'm thinking of, the scientific method. We are scientists. Space is a thing. I have hopefully shown you with these images that I've taken, and this is but a handful of images. Maybe at some point I'll actually find all the images that I've ever taken and throw them, slap them together, and kind of do a slideshow of, hey, this is Saturn. These are the characteristics of Saturn. Anyway, so where was I going with that? So yeah, so these images, and these are images that lay people can take. Citizen scientists do this, and citizen scientists have contributed to astronomy in a variety of different ways. Again, there's a lot in science, there's a lot in astronomy that is observationally expensive. The big telescopes can't do it. They don't have the resources to do this particular type of science, which is high cadence, long temporal baseline science. That is critical in YSOs, that is critical in determining the black hole masses. There are a number of different things. And pulsating variables. Do pulsating variables, how do those pulsation periods change over time? Do they change over time? Things of that nature. Those are questions that cannot be answered with conventional telescopes because we just don't have the resources. But citizen scientists, scientists with telescopes on the 6-inch, preferably 8-inch, or smaller, depending on which objects you're looking at, these people can and are devoting their time, night after night after night, looking at these objects, collecting data, and sending it to, and I will highly publicize these folks because they are awesome. This is the American Astronomer, or the American Association of Variable Star Observers. Woo! And don't let the name fool you. This is a global effort. And let me just give you an idea of what's going on here. So you can go to the site. Oops, wrong side. You can go to the site, and you can pick a star. Bum, bum, bum. Let's do Andromeda. I think I'm going to be actually disappointed with this. Plot it up. Yep, I'm disappointed with this. This is not. Sadly, Lambda Andromeda is not well studied. Let's go to one that is well studied. Come on. Boom. All right. These are observations taken by all of these folks. All of these people have contributed observations to Delta Cephei, or the prototypical pulsating variable, Cepheid pulsating variable. You can see they're U.S., Canada, Great Britain, more Canada. I don't know what a lot of these. Denmark, I guess. France. Oh, there's a French person. I think the Netherlands is also represented here. And they do this. They not only have done this for years. We're talking down here. You're talking about. This is only from. These are Julian days. In order to not deal with leap years and all that kind of crap, astronomers use what is known as Julian days. For some reason, which I have never been able to figure out why, astronomers went back in time and they said, all right, the Romans, because Romans are cool, they had 3 different tax seasons on 3 different, basically, calendars. So the best point we can start this on is when those 3 calendars converged, where a Roman had to pay 3 different taxes on the same day. Sure, why not? Let's just call that day 1. And then we have counted days ever since. So this corresponds to 2,459,700 days beyond that fateful tax-paying day. Just makes things a whole lot easier. And so you can see that this section, you're talking about years, and I'm sure there is more data in the previous to this. And some of these are visual. Some of these are just they looked at it using their eyes, and they were able to distinguish how bright the object was relative to other stars. Some of these others are more technical. They are with digital cameras and so forth and so on. So, is there still a Jimbot star? No, but there should be. Damn it, there will be. So you can do this. You can do this. You can take your own telescope. You don't even need a telescope. You can take a pair of binoculars. You can use your eyes. You can take data on these objects. You can submit it to the AAVSO. They will post it. And then other people, professional astronomers or whoever, can then use it. For example, let's go back. Oops. Let's kill this. So, where did it go? Usually not. Is it here? Nope. I think you have to actually log in. I don't know where it is off the top of my head, but there's software available for free that you can use. And there is manuals and videos on how to do this science. And there's software that they provide where you can look at the periodicity of these objects. You don't need a degree. You don't need any special training. You can do this. And we need the data on Cepheids. We need on pulsating variables, on eclipsing binaries, on YSOs. YSOs are drastically underrepresented in this database. And so this is science that anyone can do, and I encourage everyone to do it. Let's see. What do we got? So, kind of going back into this, going back to where I was talking about, is astronomers do science. And if it is simply a dome with luminaries covering it, why is it that we have paper after paper after paper after paper after paper that holds a consistency to how the universe is built, how the universe behaves, and how the universe will ultimately end? We have plausible, in some cases, very plausible, really high probability, blah blah blah. It's very, very probable that this is what's happening. That stars are in fact burning hydrogen and helium in their cores. We pretty much, unless our understanding of physics is radically different, we can basically say, yes, that is what's happening. We obviously want to keep an open mind. Maybe there's something else, but that would require a radical change in our understanding of physics. So, why is it that if these are just lights in the sky, we have disagreement? And sort of a side point is, why don't you trust me? I am an astronomer. I am telling you this is the science. I am telling you this is how the universe behaves. If you tell me that I'm wrong, A, that's rude because I've been doing this for a lot longer than you probably have. But you don't have anything to back it up. You don't have any support. You need to supply me with support. You be able to take these phenomena and explain away why this happens without saying, well, God said so, or that's just the way it is. I can tell you how this stuff works. So, if you believe it's luminaries in the sky, you need to address these data. You need to address these points. And yeah, where was I? I know there was some other point that I wanted to make, but it is escaping me. Scientific method. We are scientists. You can do this science. And if you don't believe it, trust me. Why? If I'm telling you this, and you refute it, then you're not trusting me. You either think that I am lying to you, or that I am deranged or deluded or indoctrinated, and I have been for 20 some odd years. Which is, or I'm actually telling you the truth. Which one is more likely? Of those three options, which one is most likely? That I'm lying to you for some reason, that all astronomers are lying to you for reasons. We're all deluded or indoctrinated, again, for reasons, and I don't know who it is the one that actually indoctrinated us to begin with, because as I showed you, NASA doesn't fund this stuff, not all of it. So, who is it, the NSF that's indoctrinating us? Anyway. Or is it that we actually might have a point? We might actually know what we're talking about. And that doesn't diminish you at all. That doesn't diminish your knowledge, doesn't diminish your intelligence, doesn't diminish your significance. I encourage all of you to really think critically about this. And if you're honest about it and you really have a curiosity about this, then engage with this community. Engage with the debunking community, me and others. And we will be happy to put you on the right track, to put you on the plan, to get you acquainted with the science, and to help you understand it. All right, so I am going to get off my soapbox for that. And like I said, hopefully this will turn into a series. I know there are a lot of series that I've started and I haven't done. I still need to contact. I'd like to get Coffee and Science back up and running. I'd like to get Phil Bell on here. I'd like to get PhD Tony, and I definitely want to get AB Science. I kind of flaked on him. I want to get him back on there. So yeah. I think I'm done. I think I've gone on long enough. This is probably getting on 2.5 hours long. 2 hours, 28 minutes mark. Yeah. So how are you guys? Is there anything you guys? I mean, I was at the National Mall about two weekends ago or something like that. And I had this. I am an astronomer, ask me anything. And so maybe at some point I'll do this, because I got asked a lot of questions. It was awesome. And people literally asked me anything. I had this one girl. She asked me, why do you have tattoos? I'm like, well, I like them. Then she got up to here, looked me dead in the eye, and was like, why are your eyes blue? I'm like, you'll have to ask my parents about that. She's like, you're special because your eyes are blue. And I told her she was special because there was no one like her in the entire universe. I know because I've looked. So yeah, I'm willing to hang around for a while. I'd like to hang around for a while, and if you have any questions, feel free to ask me. Or if not, then feel free to take off. I think a few of you have at this point. But for those of you who've stuck this out, thank you very much. It is appreciated. I'm glad to know that my babbling is of worth to other folks. So yeah. Pour water on a deflated football and shot it incoherently. Or put an egg in water and then pour salt on it. Carl, I would lean towards you not lying. I try not to lie as a rule. It's something that I take very seriously. So, how do the magnetic highways actually exist? That blows my mind. Not sure what you mean by that. Are we talking about maglev systems? Or... No, that's solar power. Solar-powered roads. Okay, that's a loaded question. All right. I will say right now that I have no idea what did he call it? A geomagnetic wake is. That was one of one of the Nathans, Nathan Thompson. That was his explanation for why hurricanes are a thing. Magnetic structure throughout the universe. That's actually a very, very good question, or one that I don't know the answer to exactly. But for reasons which, again, are beyond me, and probably not beyond others, but beyond me, there is an inherent magnetic field within the universe. There's just a magnetic polarity throughout the universe. It is very, very weak, but it's there. And so when we have, but when things coalesce, like clouds, giant parsec-sized clouds coalesce into teeny tiny stars, thereabouts, those magnetic fields get brought along with them. They're basically frozen in that plasma, and they get brought along. And as the magnetic fields magnetic field lines gets closer and closer together, the strength of the magnetic fields gets larger. And so that's why certain stars have ambient magnetic fields, like O and B type stars, really hot stars. When you get into G-type stars, stars like the Sun, you actually have a dynamo mechanism, very much in a roughly analogous way, very much like an electromagnet, where you have charged particles moving around in a fluid very, very quickly. That creates magnetic fields. And so there are a couple of different ways that magnetic structures are through the universe. But I don't know the answer to, and I should probably look this up. I mean, hell, I read it out of my linear algebra text. I don't know off the top of my head why the universe started with an ambient magnetic field. Mm-hmm. Thank you, Dora. I really want, obviously with, flat Earth, but I think this is in general. And sadly, there was a Gallup poll in this country done, and it's done every year. And it basically ranks the public's trust in 14 different institutions, like small business, military, Congress, courts, things of that nature. The only two of the 14 that are above 50%, where majority of the population actually trust them, are the military at 64% and small businesses at 68%. Everything else is either below 50 or well below 50. What this tells us is that yes, AB Science, his dissertation is on magnetism. That is his bread and butter. But what I was looking at when I first got into the flat Earth sort of community or debunking community or what have you, I quickly came to the realization that this was really just expert denialism. When you go up to someone like myself and you say, you're not a scientist, your field of study is not worthwhile, it's pseudoscience. What that really is saying, you're an expert and I don't believe you. So it's expert denialism, and it's grown. It is basic. I don't know if it's blossomed. I won't say that flat Earth is the kernel of it, but this distrust of experts seems to have ballooned outward. Probably motivated by COVID. Probably motivated by, I guess I shouldn't say the C word on YouTube. Motivated by the Rona. Motivated by the lie about the U.S. 2020 election. All of these things just lead to a degradation of trust. And I think the only way to regain that trust is to be transparent, is to show what is going on, and show people how, not really just the science of it all. Obviously, I don't expect a layperson to be able to read this paper and actually get anything really out of it, to be able to really understand most of it. I'd like to think that my writing style is so eloquent that anyone could read it and get stuff out of it, but I won't be so vain. Showing them the science in this way is one thing. But I think what we need to do is we need to show folks how the science is done, how the science is funded, and why we do these things. Because I think that's the only way to establish trust, to reestablish trust. Obviously, it's not going to be 100%. You're always going to have people on the fringes. But this is why I do this stuff on YouTube. Is I want to educate folks, but I also want to help reinstill trust in experts. Because when I was in my 20s, there were studies done like, how well do you trust doctors? And that was like in the 80s and 90s. Like, doctors were pretty much the trusted people in the world, or in this country. Now, I think it's less than 50%. Politicians were down, obviously. Lawyers were also down. Auto mechanics were way down. But doctors, right at the top. Below them were scientists, just kind of general scientists. So, and now it's drastically different. Within 20 years, it's really gone downhill. And so I think that in the debunking community, I think there really needs to be more of an effort to regain that trust. I mean, obviously, the people are in this game for a variety of different reasons, point and laugh, or they're beating their head against the wall, trying to convince these folks like Bev that they are wrong, and this is why they are wrong. But I think, as a general rule, the way I'm going to approach this is I think that we need to, again, reestablish trust. And the only way that can be done is through transparency and through asking questions like, why do you not trust me? What is it about me that makes you think that I am lying to you? So, science is way above what ordinary people can comprehend. So I had a choral teacher. I took chorus when I was in high school, and on the first day, the chorus teacher told me, "Give me enough time, and I can teach this pencil how to sing." And that is stuck with me, because obviously his point is obviously a pencil can't sing, but what his point is that given enough time and an active, engaging learning experience, if the person wants to learn, then you can teach them, and they will learn it. So it boils down to, the way I see it boils down to two things. It boils down to how intrinsically good are you at certain things. Obviously, Clive is way better at math than I am. Just leaps and bounds better at math than I am. But that doesn't mean that I can't get to Clive's level. It just means I have to put a lot of work into it. And so it really comes down to how much work do I want to devote to this to get to Clive's level. And as it turns out, I'm not overly motivated to do that. I have other interests that I'd like to get into or like to keep up with. But that's what it boils down to. When someone says, I can't do science, or I don't understand science, what they're really saying is that I don't have a good intuitive grasp of the subject, and I don't want to put the time into actually learning it. It's not that you can't learn it. I can teach anyone. I can teach anyone astronomy. I can teach anyone physics up to my skill level. I can teach anyone calculus up to my skill level. Any subject that I have, I can teach anybody up to my skill level if they are willing to learn. So, certain aspects of advanced science, yes, basically, I definitely will agree with that, because folks are they're just not interested enough in it. They're not willing to put in the time and effort to learn that sort of stuff. So, Tusk, you went to the shop. What did you buy? Did you buy me anything? Did you buy me a dragon? Dora, I have no idea how my students experience my lectures, because they don't comment on my lectures on YouTube, and A few actually have come up to me afterward and told me they appreciate the way that I teach, but I don't know if that's out of it's a handful out of 250. So I don't know how representative of a sample that is. So. What makes Flirts think that they are so special that scientists need to prove themselves to them? I say let them be the village idiots. The rest of us will just move on, and leave them behind. The what's the word? What I'm afraid of in taking that mentality, Jeff, is it seems like it's getting larger than just the science denialism is getting larger than just the corners of society, the fringes of society. It's becoming far more mainstream. And this is something that we need to really address. And the thing that actually is starting to keep me up at night is climate change. We as a society are effectively doing nothing to prevent the death of our own species. And a good fraction of that is, well, some of it is laziness, or just not giving a shit. But a good fraction of that is just not believing that it's actually happening. Either that it's happening at all, that we're causing it, or it's happening on the time frame that that scientists suggest that it is. And so, I would say with the flat Earth community, there are a number of them. Yeah, I mean, if they don't want to learn, then what can you do in that situation? But as a general rule, I think if someone denies experts, scientists, doctors, what have you, we do need to do something to sort of address that problem. Or literally, and this is not hyperbole, I think if we do not address that problem, our society or our species is in for a world of hurt, a spherical world of hurt, to the point that it might actually lead to extinction. Again, I don't believe that is hyperbole, sadly enough. Dora, one of the things that I do not do, and if you do this for me, please don't tell me this, there's something called Rate My Professor. I think it's actually ratemyprofessor.com. You can put in the name of any professor, and it will literally, it's basically a database of students getting on there and saying, this guy's great, this guy sucks ass. And I have only checked it once, and that was like 10 years ago. Obviously I hadn't taught lectures for very long at that point. I think I had like a low B. And so I do not know what it is. I do not want to know what my grade is now. I'm pretty sure I am very well aware of my shortcomings, and my fragile ego just can't take it. Would the world be worse off for not having humans on it? I don't think the world would care. I mean, the world is basically just a giant rock with a thin biosphere over it. Ultimately, the world is going to become a desiccated husk, and is ultimately then just not going to exist anymore. So, I don't think the world would be worse off if we weren't around. I mean, hell, it had dinosaurs puking on it at one point. So, who knows? Hey, Dr. Nimrod, Your Holiness of baconness, I don't know. Too tired to come up with that. Solution to global warming: open one of the dome windows. Yes, it always reminds inevitably when folks start talking about the dome, I just go to Spaceballs, and I'm like, all right, well, if there's a dome, is there a giant robot with a vacuum cleaner out there to suck everything out? I don't know. Yeah, I see. For there, Jeff, I I go with, again, the question of why. Um, is that why aren't they accepting these things? Why are they basically, I'm not hearing you? Why are they saying that what I do is fake, or the gravity ain't a thing? I mean, why do they hold to this? And they hold to it so vehemently. I mean, yes, some fraction of them are trolls. Some fraction of them are just doing it for the lulz, and they just get a kick out of riling up people or getting attention from folks on our side of things. Well, I hate saying our side of things, on the mainstream side, on the science side of things. But I really want to know why these folks hold to this. Why are they denying experts? I personally think it has to do with they feel a lack of significance within their own lives, but that's probably a little too armchairy psychologist to me, but that's kind of where I'm leaning towards. There's more than one parks that are plausible. There's more than one. Well, sadly, not only does it list Rob Parks, but it also lists the institution. So if you were to look at Rob Parks, George Mason University, then I am the only one, as far as I know, I am the only one here. So, His Bacon Holiness will do necessary, or Dr. Bacon? Dr. Bacon? Dr. Holiness? Will Dr. Holiness work? We'll call it Dr. Oink. I do have to say that bacon is the worst part of the pig. I do not like bacon, which is amazing because I like every other part of the pig. I haven't tried pig's feet, but I'm sure I'll like it. I haven't had chitlins. I'm pretty sure I'd like it. Jimbo Parks. Oh, that I might actually look up. I might look up, rate my professor. I might see whether or not there is actually a Jimbo Parks out there, Jim Bob Parks out there, and how well of a professor he actually is. But who knows? I think I can make a bigger contribution to the fight in my classroom. The village idiots have given up on learning. Yeah, I agree, and I think that, and this is the tremendous amount of respect I have for teachers, particularly at the early stages, like first to say fifth grade, because that's where certain principles get instilled. That is where the trust gets instilled. That is where the thirst for knowledge gets instilled. I mean, yes, you can obtain these things later on, but if you get them then, again, this is my non-expert opinion, they don't lose it. They don't lose these things later on. If you can train them right, if you can indoctrinate them, if you can instill passion, if you can instill trust in them, then you're doing a fantastic job, and I'm sure you are. So yeah, I have tremendous respect for teachers at that level, because I couldn't do it. I couldn't find the energy to do it, and yeah, the responsibility of it all, the responsibility of having these young minds, being able to shape them and put them on any particular path. That is a responsibility I frankly do not want. So right now I just deal with millennials. And people were like, I just want Gen Ed credit. So I just try to get them through that as much as possible. Pig's trotters are delicious. No idea what a pig's trotter is. Pig's ears. I have tasted pig's ears, basically what you give a dog, and I didn't really dislike it, but pretty sure it's treated so that the dog will like it. I don't know. Isbian is tops. No idea what that is either. Make Isbian. Is that like I am a jelly donut? can't remember what Kennedy said. Whatever. Yeah, I can't remember. Pig feet. Pig's feet. Yeah. I would be down for seeing you watch cook up some pig's feet. I've never had the opportunity to eat pig's feet. But I'm fairly certain I'd like it. Things they try. Yeah, okay. I've been up for a really long time, so you'll have to forgive me for not, picking up on trotting feet, that sort of shit. Here you go. All right. Well, I'll just click on it. And I'll mute it. What happened? I don't know what just happened. I clicked on it and it did that. I can no longer see the chat. What is going on? I can't see what people are saying. I'm stuck with this YouTube thing. Let's do that. Let's go over here. Let's reopen the chat. Hey! Got it back. Alright. Today I'm making grilled mackerel with saffron rice. That sounds intriguing. I still have to make that haddock for Crafty at some point. Let's see. Roughly 40 years I've listened to a group of elderly men discussing how ship made of steel can swim. They've concluded it's because surface tension. Sure, why not? Well, according to Sleeping Warrior, that is the start of the Iron Age. Is when the ships were made out of metal. Isbian during my last visit to Berlin. I have never been to Germany. I would like to go to Germany. I have my good bit of my family back in the day are Germans. I don't claim any sort of German identity. I just, I have relatives with the name of Volkenhorst and, what was the other one? Hessian? I don't know, Hessian. Oh, well, and my mother's maiden name was Zimmer. So, there you go. Saffron is not overrated. It's one of my favorite things, particularly for rice. Your face is overrated. I don't know. I've never seen... No, I have seen Nimrod's face. Normally, I'm looking at the kitty's face. Kitty's face is definitely not overrated. You know, if the flip side is looking for a guest host, I am almost 12 hours away from you, Reason. Not that, I'm trying to get on someone else's stream or anything, but, just putting it out there while Crafty is maternally leaving, or left. His name is Parks. He must be of Korean descent. It's interesting. You should say that because folks tend to say that I'm of British descent because of Parks. And actually, even though I explained what I'm about to explain to my ex-wife, she still got me the Parks coat of arms, the English coat of arms for Parks. As the story goes in my family, Parks is a shortened, anglicized version of Parkinson. So, according to my dad's side of the family, my lineage is half German, half Swedish. And essentially the patriarch, the person who came over on the boat, when he died, he had 4 sons. They all signed a guest registry, and they all anglicized their name in a different way. You had Parks, like I spell it. You had Parks with an ES. You had Parker, and then I can't remember the 4th dude, what he did. But none of them really wanted to keep the name Parkinson. So apparently, according to family legend, I am of Swedish descent. I do have English on my mother's side. My mother's side is basically half German, half English. As far as we can tell, it was a goal of my mother's to eventually get over to the UK and continue on the lineage to see if it is solely English or if we had Scottish blood in us at some point or what have you. So, Jim Bob Parkinson. Yeah, I really should not have told you guys that. Great. How do you feel about chocolate mousse? Pretty good. The antlers tend to get in the way, but generally speaking, I do like chocolate mousse. I haven't had it in a long time. I do like German chocolate cake, which, from my understanding, is not German, but it's still yummy. I like me some coconut. Yep, sounds like you're Swedish. Yeah, well, I'll take it. I like Sweden. I like is Mads Mikkelsen Swedish? Joel Kinnaman, I think it's Swedish. The Skarsgårds, I think, are Swedish. Although, hell, I could just be being a brutish American and just saying, oh, all Scandinavians are fucking Swedish. Chocolate is not horrible. I think chocolate is overrated, but chocolate is good. Chocolate is good. I actually prefer vanilla over chocolate, but, I'm just a vanilla sort of guy, apparently. Mousse. Yes, I remember that. I knew there was someone in our community who actually makes good German cakes, and I think that was the person who told me that German chocolate cake is not, in fact, German. Yes, with real mousse. You have to be very careful about de-antlering the mousse before you chocolify them. But yes. Better than chocolate mouse? Chocolate covered meese? No, I don't think I would go that far. Alright, well, I think I'm coming to 3 hours of this stream. There's a moose loose about this hoose. I would say that I should probably go to sleep because, like I said, I've been awake for a really long time. I don't know if I've been awake for 24 hours yet, but probably close. I don't think I'm going to be able to go to sleep anytime soon, but I am rambling now, which is a good sign that I'm, done. All right, Crunchy Frog. I don't get Crunchy Frog as a reference. That just makes me think of Harry Potter, which makes me think of J.K. Rowling, which makes me sad. Okay, yeah. Like I said, thank you all for being here. Dora, for some reason I can't take naps. I am incapable of taking a nap. I think it's because my head, I know I'm napping. I know that I will have to wake up soon. And so my body's like, why bother? And I'm constantly thinking of, why am I not asleep? I only have a certain amount of time to sleep. And it ruminates, and it just keeps me up. And so I literally cannot nap. When I go to sleep, I'm long haul. I actually, to the point where I really can't set alarms. So I just have to make sure that I go to sleep well before I am due anywhere the next day. because, yeah, I don't work well with alarms. Night pawn, night mon, night chip. I think that would, no, I think that's, what the fuck? Oh my god, the Waltons. John Boy. That's John Boy. It was Night John Boy. Naps can be several days long. I refer to those as comas. Yeah. Oh, that reminds me. And I know this is way out of left field, but I'm tired enough that I don't care. So, a roommate in college, best friend. So, what I don't remember what I was doing. I kind of lost track of him for a day. We were, like I said, we were roommates. This is our freshman year, and yeah, like I said, I lost track of him for a day, or basically a day. I come home, and I think I'm trying to go to sleep. It's like maybe 11 or so at night, and he comes stumbling in, drunk off his ass, just completely wasted, and he lays in bed. And he's like, I turn off the lights. And he's like, no, lights are, darkness is bad. Darkness is bad. Makes me want to puke. Turns the lights back on. And some reason, I don't know, I can't remember the next part of it. I eventually leave. I go to class. I do the whole thing, my entire day. I come back in the afternoon. And he's literally, the lights are on. He's literally sitting up in bed with a trash can, which I could smell before I entered the room, sitting in his lap. I did not risk actually looking into it. And he's sitting there sleeping. Just like that, with the lights on. I'm like, all right, well, I ain't going to touch that. I want nothing to do with that. So I think I leave again. I'm like, all right, I'll go find something else. And I come back, and he's still like that. The dude slept for 26 hours, sitting up with a barf trash can in his lap. Oh, no idea why I'm telling you all this, but all right. Good night, all. Let me see if I can figure out how to stop this. Without breaking stuff. All right. Yeah, go ahead. All right. Peace out, everyone. Like I said, I am e-begging. Please disseminate this to whoever you think might find it interesting, particularly if they're a flat earther. So, not asking for money. I'm asking for exposure. It's different, right? It's a different sort of thing. All right.